Right, latent heat next. Doing okay, Siva? Doing okay? Kim? Yep. Alright, latent heat, you got that? Yeah. Okay, so, let's continue. So, let's imagine you have a block of ice, and this ice is slowly being heated. That is, you put some heat energy in every unit of time. Maybe, for example, you put 4,200 joules of heat per second into the ice block. That's a power of 4.2 kilowatts. So, the temperature of the ice will obviously increase as you put a little heater under it. Let's have a look at the temperature against the energy graph. So, on the bottom is how much energy goes in, and on the side is the temperature. Okay, so, at the beginning, when you put no temperature in, let's imagine the ice is at minus 100 Celsius, so it's very cold. Then you put in more energy, 500 joules, 1,000 joules, or whatever it is. So, you can see that the temperature increases. But then something very strange happens. It increases, and then it stops increasing. Even though you're continuing to put heat energy into the ice, it's no longer getting warmer. And then it starts to get warm again. And then here, nothing changes. You keep putting energy in, and the temperature stays the same. And then eventually it begins to change again. Now, if you look at the temperatures when this leveling happens, you might figure out what's going on. So what do you think is happening here? Melting. Yeah, melting. And then at the 100 mark? Boiling, evaporating, yeah. So what's happening is the heat energy stops increasing the temperature and starts to change the state. Okay, so if this was a liquid and I put heat into it, it will get warmer and warmer. Then it will stop getting warmer at 100 and will start to change into steam. Okay, so you need energy to change the state. If you want to go from solid to liquid, you need to put in energy. If you want to go from liquid to gas, you need to put in energy. If you want to go from gas to liquid, you need to take out energy. And if you want to go from liquid to solid, you need to take out energy. Okay? So, they sometimes like to ask students in the exam to draw a graph like this. So what they want to see is that you can draw a line here at 0 and a bigger line here at 100. The meaning is this. It takes more energy to change it from liquid to gas than it does from solid to liquid. Okay? So like here, 1,000, 3,500, so like it takes 2,500 kilojoules, whereas here it only takes like whatever, 100 kilojoules. Can you copy this and make sure that you draw this longer than this? Okay? They're not so worried about the scales. What they care is that this is longer than this, and that this is at 0 and this is at 100. And that this is temperature and this is energy. Now, see where you drew this? Did you mark off 0 and 100? And you drew the second one longer than the first one? Yeah. Okay. And did you write in temperature and energy? Good, okay. Okay, good. Don't worry so much, Chow, about the numbers, okay? The only numbers that are really important is the 0 and the 100. Okay. Okay, continue. Yeah. And then you have this graph?
Yeah.
Yep, okay. So this gives us our concept we call latent heat. This is like the energy you need to change the state. Okay? So, in the graph, which latent heat was bigger? To change it from solid to liquid, or to change it from liquid to gas? Liquid to gas, okay. So latent heat, the definition is the energy required to change the state of a unit mass, and this part's important, without a change in temperature, okay. So the latent heat is how much energy you need to change 1 kilograms of mass's state, but not to change its temperature, only its state. Okay. Now in the exam, it's very, very common for students to forget to write about the temperature. So in the exam, definition, what is latent heat? Students will write the energy required to change the state of a kilogram of material. And they forget to write without a change in temperature. So, if it's a 2-mark question, you only get 1 mark. Okay? So please, don't forget, you can't change the temperature, just change the state. Alright. So carefully write this down. What's wrong, Siba? Are you sure? Did you write all of this down? Every single word?
Energy required to change the state for unit mass without changing the temperature.
Yes, that will do. I wonder how many of you will forget to say without changing the temperature in the exam. I'd say, I'll go with 3 of you. That's my prediction. Now which 3, I don't know. But I'll say 3 of you. No. It's random. I don't know which 3. You could be, any student and you could forget. Like even the biology teacher, when I was talking to him about it, he forgot to say without changing its temperature. It's I don't know why, it's just easy to forget because people think, oh, it's changing the state, done. And then they forget to say without changing the temperature. Okay, have you got that? Yeah. So, latent heat comes in 2 types because you can go from liquid, you can go from solid to liquid, or you can go from liquid to gas. So because there's 2 types of latent heat, we give them each a name. So the first one is latent heat of fusion. So that one is, well, think about the word fusion. Well, maybe you could guess which one it is. The solid liquid one. So that's melting. And then latent heat of vaporization, which one's that? Yeah, so what verb in English describes going from liquid to gas? Evaporation. No, keep it simple. Simple English word. Look at what I used for fusion. I said melting. Simple English word. Simpler. Boiling. Thank you, Chow. Boiling. Good man. Right, can you write these 2 down? Got that? Yeah? Got that? Continue? Yeah? So, just like in the last lesson, we have a formula. It's not very difficult. Imagine you have m kilograms of something and you want to change its state. How much energy do you need? It's simply mass multiplied by latent heat. Simple. Why is there no delta theta here? That's right. So, the formula is just ml. Okay. Right, can you write this formula down? This is the latent heat formula. Oh, by the way, what's the units for latent heat? Look at the formula and tell me. Say again, Siba?
Kilograms per
Yeah? Yeah? Are you guessing or are you looking?
joule?
You have it half right, you just have it upside down.
Joules per
Joules per kilogram, yeah. Because look, if you put the m underneath here, you get L equals Q over m. So L will be joules over kilograms, joules per kilogram. Okay. You got that formula? Yeah? Right. Now, you don't have to write this down. I just want to make something very, very clear. Very clear. Okay, so listen carefully. Water will freeze at 0. You know this, obviously. And water will boil at 100. You know this, obviously. Now, what you do need to write down is the next thing, which is the values. So, if you want to melt ice, you need fusion, latent heat of fusion. And that's a pretty big number. That's 334 kilojoules. So it's actually 334,000. Now just think for a moment. What was the specific heat capacity? It was 4,000, roughly. Something like this, yeah. But the latent heat is 334,000. In other words, it takes much more energy to melt ice than it does to just warm water. It actually takes a lot of energy to melt a kilogram of ice. Now that's good news, because it means when you put your ice in your cold drink, it stays ice for a long time. Okay, so kind of good. The other one is vaporization. Now, will this be bigger or smaller? Bigger. Now, this is already pretty big. It's 334,000. So it's 2,265,000, because it's 2265 kilo. You need 2 million joules of energy to change liquid into steam. That's even more. Okay. So if you want to make steam, you need a lot of energy. So when you think about the train that's moving and it uses the steam to push it along, there must be a lot of energy inside the train to do that, So just remember that water could be a liquid at 100. In fact, it is a liquid at 100 until it gets enough energy to become steam. Let's just say steam and not stream. Likewise, water could be a liquid at 0 until it loses enough energy to become ice. So just because it's 0 doesn't mean it's ice. It could still be a liquid. And just because it's 100 doesn't mean it's steam. It could still be a liquid until it converts. Okay. So what I need you to write is just these 2 points here, these 2 values. And please, it's kilo, so it's 1,000. So these are thousands. So it's 334,000 and 2265,000. These are the values.
just write the ones down there as well.
No, I just need the 2 bullet points, number 3 and number 4. That's all I need. You don't, yeah, just these 2, Chow, yeah?
Mhm.
Yeah. You got that written down? Yeah. Chow, do you have this?
Yep.
You sure? Andek?
Yeah.
Yeah, okay. Right. So just to make the last point very clear, imagine you put minus 20 Celsius ice in the microwave. What will happen to the ice? So first it'll be at minus 20. Then some time will pass and it'll be at 0. Now it's still ice. It will remain at 0 for some time and then it melts. And now it becomes water. And the water is at 0. And then what happens? The water will warm up until it's 100. It remains liquid for some time until it boils. Then it becomes steam at 100. And then the steam warms up. And then the steam leaves the microwave. Okay?
So would this be an example question?
No. I really want to drive home the point that just because it's 0 doesn't mean it's liquid or solid. It's not clear. Okay. Here's one I want you to try. I want to know how much energy you need to change 1 kilogram of ice at 0 Celsius to 1 kilogram of steam at 100 Celsius. So, yeah, there's 2 conversions that happen. First, it goes from solid to liquid. Then it also goes from liquid to gas. But don't forget, in the middle, it has to warm up from 0 to 100. So there's actually 3 stages. Yeah? Stage 1, solid to liquid. Stage 2, 0 to 100. Stage 3, liquid to gas. Okay, see if you can get me the answer. See if you can get it. You'll need the formula from the last class too. Should be a huge number. What you get, like 3 million or something? Oh, okay. A big answer?
317 kilojoules.
So 3 million. Yeah. That's a lot of energy, isn't it? let's have a look at the answer. So, we've got first solid at 0. Then it becomes liquid at 0. Then it becomes liquid at 100. And then it becomes steam at 100. So I think of it as 1, 2, 3 stages. Stage 1, stage 2, stage 3. So in this stage I need to use the formula ml. Here I need to use mc delta theta, and here I have to use ml. Okay. So the total energy will be ml1 plus mc delta theta plus ml2. There's two L's here. Okay. Now what's the m in this question? 1. So that's kind of nice, isn't it? Right, so L1, the latent heat of fusion. What is that for water? 1000. Yeah. Plus 4181 times 100 plus 225? 225? Oh, is that right? 2265. Oh, 2265. Oh, yeah. So you have the final answer there, Matt. What did you get? 3017. 3 million, yeah. What's after the 3? 3017 kilojoules. Yeah. So that's 3 million, you're right. So that's 3.01 megajoules. 3 million joules. Okay, that's a lot. A lot. Oh, sorry, I only increased by 100, not 1,000 Celsius, yeah. Okay, I hope you got that. If you didn't, can you write it down? And then we'll continue. Got that? We'll continue now. Chow, are you writing this down? Yeah? Yeah. So they get a little bit harder than this, I'm afraid to tell you, because you can have some questions where you have some water and you mix some ice in it, and then you mix it and the ice melts and all this stuff going on. So let's have a look here. This is it, yeah. So you have 200 grams of water and you add in 10 grams of ice and you mix it all together. How much energy will be required to bring the mixture to 10 Celsius? Right, so you have some water and you have some ice floating in it. And you have 200 grams here and you have 10 grams here. And you put some heat into it. Now, before I start, what is the temperature of the water and the ice? And I'll give you a little clue. I say they're mixed together and reach thermal equilibrium. So what does thermal equilibrium mean? Do you remember? Both the same temperature. So what temperature must that be? Yeah, must be 0. Good. So must be 0 and 0. Okay. But I put some heat into it, and the temperatures both increase to 10 and 10. And my question is, how much energy do I need? Right. So let's do this one together. Two things gain energy. This water gains energy, how much energy does it get? It's mc delta theta. What's that? 10. Okay. Now, what happens to the ice? Two things happen to the ice. What's that? What happens to it first? It melts. So that's ml. What's it? 385? 334 for melting. Yeah, 334. 000. But then after it melts and becomes liquid, what else happens to it? No, not quite yet. It doesn't evaporate, it becomes a liquid. But what happens to the liquid? Yeah, not boils, but it doesn't quite reach 100, it's only going up to 10. So it warms up to 10 Celsius. So that's plus M L delta theta. Okay, so this is the water, and this is the ice when it melts, and then this is the melted ice, which is now water, and this warms up. So the water warms. So three things happen. The water warms, the ice melts, and the melted ice warms. So if we hit this in the calculator, we can get the answer. Whatever this is. Actually, I think I've got mine open now. No. Um, 12120. There you go. Happy? Got that?
What is the 481 value for?
4181 is the heat capacity of water. Okay, continue. See that? Yep, no problem. Okay, we're okay.
334000.
Yeah.
Oh,
Yeah, that's here somewhere. Where'd you write it?
this one?
No, the next. Where'd you write it? Oh, here. That one.
Oh.
Yeah.
Okay.
Okay, continue. See that? Yeah. Right. Some ice is mixed to some water, and you mix them together until the ice melts. What is the final temperature? So this one's a little bit like the question we did with the coffee and the milk, and you mix them together, get the final temperature. So you have some ice of 0 Celsius, and then you put that into some water of 330 grams at 15 Celsius. Okay. And then what you do is you mix them together until all that's left is some water of 5 Celsius. Now that kind of makes sense. You know, if you put ice into warm water, then the result is you have colder water, because the ice, brings the temperature down. So my question is, how much ice was there? So I want to know how much ice there was. So we'll say that there was X kilograms of ice at 0 Celsius. Okay. So, in this picture here, does the ice gain or lose energy? Gains, good. And the liquid water loses energy. And because this is in a cup which is closed, the energy is not coming in or out, so the gain in the ice must equal the loss in the water. Okay? Right, so let's figure that out. The ice gained energy. So what happened when the ice gained energy? Two things happened. First it melted, and then what happened after that? It warmed up, okay? So what's the formula for how much energy it needed? ml. The m is x, and the L is 334. Then what happened to the ice? It melted, became liquid, and then it warmed. So it's still x, then it's 4181. Now what's the delta theta? No, and no. 5 is the only number left. Think about it. The ice, when it melts, it's 0. And then after it melts, it goes from 0 to 5 is at the end. Okay? So it's 5. Right. Now, that came from the energy lost by the water, which is M, C, and how much temperature change was there? Yes, because it went from 15 to 5. So that's 10. Yeah? And you realise, oh, this question isn't so hard now, because again I can solve for x. And that will be 334000x. Siba, can you tell me what 5 times 4181 is? And Mark, could you multiply these three numbers, please? These three?
20905.
20
905.
x. And then, can you add these two numbers together? Okay.
13797.3.
Like this? Okay, that's what you get there, Siba.
354.
Yeah.
905.
X equals 13797.3. So maybe Chow, you could just divide this here at the end. Should be a small number, yeah.
0.038.
38. 388 kilograms. So that's equal to 38.8 grams. Which kind of makes sense, like, you know, small amount of ice, 40 grams. So you needed 38.8 grams of ice is the answer. Now, what I find strange about this question in the exam, you know, this is a section B question, so maybe it's like 5 or 6 marks. Most people get it wrong. Even though, I don't know, I don't think it's that bad. What do you think? Is it that bad? Andek? Siba, what do you think? No comment, or? I mean, it's not the worst. It's not like a mechanics question that was very hard, you know? So I have seen this one in the exam a couple of times where they ask the student to work out how much ice you need to put into something to bring its temperature from 15 to 5 or whatever it is. So it's a standard latent heat question for the exam, very standard. Yeah. Okay. You have that, Joe?
Mm-hmm.
It's a Stephen question. It's a Stephen question, and I don't know if you really want to see it or need to see it. I'm sure I have a question like this in the workbook, so I could do it in the tutorial next time. Because no, we won't bother with that. When's our next class? It's Physics Friday. So it's a double class, yeah? So, do you want one or two tutorials on Friday?
I think one should be enough.
One should be enough? Okay. Yeah, because we're doing all right, because next week we'll finish materials and start electricity, which is the last chapter. Electricity is a little bit bigger though than the materials. Yeah. So we're doing okay. We'll get some revision in at the end, I think. Yeah. All right, we'll wrap it up there. If you can try your best to finish these for Friday. Oh, and don't forget, Thursday is the assessment support, isn't it?
Yeah.
Yeah. It's going to be the last one for the physics, because we're about ready to submit the final one. Okay. So I don't know if you want to do. I'll have to talk to you about if you want to do anything else in that time, or if you just want to sleep. We'll talk about it on Thursday.
What about the essay?
The link is on Moodle if you want to upload the draft.
Today?
Today, please, or tomorrow morning.
Okay. The same.
Yeah.